Good afternoon. My name is Monica Martinez, and today I'm presenting on relativity, a challenge to reality. Most people hear the word relativity and think of complex maths or black holes. But at its heart, it challenges the very foundation on how we define truth and existence. Is there a world there that exists the same way regardless of who is looking at it? Or is reality something we co-create through our own perspective and motion? Today, we're going to walk through the journey of an observer-dependent universe of Albert Einstein. To understand this challenge, we first have to look at Einstein. Einstein introduced through his theories special and general relativity, theories that redefine our understanding of cosmic process and geometry of the universe itself. Before this, humans operated under a set of obvious philosophical assumptions. Relativity shattered those assumptions by suggesting that the cosmic process we observe are not fixed, but are intrinsically tied to the observer's perspective. Okay. To understand why Einstein was so radical, we have to look at what he replaced. And for that, we have Isaac Newton and Immanuel Kant, who were mostly world dominating on their theories. For Isaac Newton, he believed in absolute time, a universal clock that ticks, the same for everyone. For Newton's, the now was a global moment shared across the entire universe. For Immanuel Kant, on the other hand, look inward and argue that space and time aren't things we find in the world, but rather a priority intuitions. They're not things that we discover, but the lens through which our minds must organize experience. So, for example, for Kant's theory, it was like we already have that instinct in our natures that we already know what we know already, like with surviving and with our needs. It's mostly like that. But Einstein will eventually prove that both were half right, but in many ways, but they were fundamentally wrong. Right? In 1905, Einstein introduced special relativity, and it all hinged on one shocking discovery: the speed of light is constant. Right? For the core of Einstein's challenge was the discovery that the speed of light is always constant, regardless of how fast an observer is moving. The scientific fact necessitates the breakdown of absolute simultaneity if light speed is fixed. Then time and distance must stretch to compensate for motion. Right? For just a small example that I thought it would be nice to add, even though it's not in my PowerPoint, is in our daily lives, if you throw a ball at 10 miles per hour while standing in a train moving at 50 miles per hour, a person on the ground sees the ball moving at 16 miles per hour. It's simple addition, but the light doesn't work that way. No matter how fast the observer is moving, light always travels at the same speed. This creates the massive problem for Newton's absolute time. If light speeds cannot change, then time and distance must change to keep the math working. This is what we call time dilation and the link contradiction. This isn't just optical illusion, and it's physical reality where time is actually slows down for an object's motion. A nice fact I've seen through my research that I've done for this presentation. Right. Next, we got practical definitions. Physical to conceptual. Hence, Richabach argue that space and time definitions are coordinative. We link physical objects to fundamental abstract concepts to measure reality. In observer subjectivity, Since definitions depend on coordination, the present may not belong to the universe at large, but rather to how individual mind observes a specific event. All right, let's look at a practical example of this perspective shift with this example that I made. Um, Imagine a bus moving at a constant speed. A person inside the bus, and there's a person outside the bus. They both see light differently based on their motions they're at. The key takeaway is here is that there is no universal now, but what it feels like the present to you may be the past or future to someone else moving at a different velocity. Right. Now we're moving on the whole argument, challenge to space-time sustainabilism. Right. So we start now. What's the whole argument? This was proposed by Albert Einstein during the time he was looking for an answer for general relativity. It considered a matter-free region of space-time the whole. Same conditions outside will possibly be in the inside. His conclusion at the time, he was like, no, it violates determinism. So I don't think it will work like that. But I got a quote from Norton. I think it was very important to highlight. Later in 1913, he sought to transform his failure into a victory of sorts. He thought he could show that no generally covariant theory at all is admissible. Any such theory will violate what he called the law of causality. We will now call it determinism. He sought to demonstrate this remarkable claim with the whole argument. Right. I also added a quote from our book with Einstein's special theory of relativity. We can see that some of the beliefs we had long had and that most of us took as obvious empirical facts turn out to be mistaken. In this way, relativity theory forces us to rethink some of these long-held beliefs. Right, understanding space-time, and this is a summarized table from Norton. And for each stance, there's substantialism, relationism, and Leibniz equivalence. And I separated for core belief and view of the whole. Starting off with substantialism, space-time is a physical matter or substance that exists independently. Points in space have their own identity even without matter. For relationism, space and time are only the relations between physical objects. Without matter, space-time has no identity or meaning. Leibniz equivalence, mathematical different models can represent the same physical reality. The whole transformation doesn't change the physical state. Right? For capacity for predicting events, the whole argument shows that if we treat space-time as physical substance, so stabilism, we lose the ability to predict the future with the theory of general relativity. For this part, I did it on placement, based on placement and what's best and what's not really related to that sequence. So first is relationism, Leibniz equivalence. Second, Newtonian absolute space. And then third, space-time substitutabilism. General relativity fails to predict the metric inside a whole if points have their own independent identities. Right? Also got a quote for John Norton on Leibniz equivalence. One line of thought simply agrees that the whole argument makes an acceptance of Leibniz equivalence compelling. It seeks a single mathematical structure that represents a physical space-time system. Right. For the conclusion, redefine reality. First, perspective shift. Modern physics doesn't just change details about space and time, it challenges our whole perspective of reality. Second lies loss of identity. Space-time does not have an identity of its own. It is defined through matter and coincidence. Third, a unified view of space and time cannot be preserved as independent identities, must be understood as a dynamic relational set of space-time. And the last one will be philosophy and science. Philosophical acceptance of Leibniz equivalence is required to make sense of the math in general relativity. For all in conclusion, relativity is more than a set of equations, it is a redefined reality. It teaches us that many things we took as obvious empirical facts are actually mistaken by forcing us to rethink long held beliefs about time, space, and the observer. Einstein didn't just change physics, he changed our place in the universe. Right, here are my references, and thank you for watching.